Uh, Warm welcome to Support Vector's Research Paper Reading Series on Wednesday. I know that we have skipped a few sessions in the last couple of months. A part of it has to do with the fact that I've been very busy. I'm giving some time, actually, to make progress finally on my textbook that I'm writing. So one of these days it will get completed, or one of these years it will get completed. Anyway, coming back to the paper reading, the topic today is the path not taken. RLVR Provably learns of the principles. A little bit of an explanation on the title. This is actually, in my opinion, quite a significant breakthrough in research that does not come up with something too much of practical. It's not that it came up with a new model that beat the benchmarks. The main contribution is it has answered some long lingering questions about fine-tuning of models. So we'll go through this paper carefully. This research has come out of Meta and from the University of Texas at Austin, and some of the work, as for example, the first author, work done during an internship at Meta. There are quite a few authors to this paper. Now, the path not taken is, I suppose, an allusion to Robert Frost's poem, "The woods are lonely, dark and deep," and so forth. The RLVR probably learns of the principles. RLVR phrase stands for reinforcement learning with verifiable rewards, of which GRPO is sort of the poster child, and DAPO, that has come out of it as an evolution. These are examples of RLVR. The GRPO, as you will recollect, was foundational to DeepSeek R1. DeepSeek R1 was important because it was the first research paper that showed how you can induce reasoning in machines. So, obviously, this paper will talk upon some crucial topics. I'll give a little bit of a background. If you feel that we have the background, I would love to have this session interactive and move faster or slower based on your feedback. This will be a little bit of a hard paper reading for me because I have no idea how much preparation or background you are bringing to the reading of this paper. If you have already read this paper, I would love to hear what you, or even glanced at this paper. I would love to hear what you have thought, what you, which parts you liked. So before I start, would anybody like to reflect upon it, or if anybody has looked at this paper? Okay, so then I will get started. I will break it down as before into a few parts. So what is the problem that they are trying to solve? I'll give you an idea. Today, we have the so-called, what has become for training of LLMs, the three steps are typically pre-training, and this is the Instruct GPT, for example, pipeline. It says pre-training of LLM, followed by supervised fine-tuning. And this is typically followed by RLHF, reinforcement learning with human feedback. This is the traditional Instruct GPT pipeline. Somewhere along the line, when DeepSeek came along, they had an alternate pipeline which basically said start with this, pre-training. That remains. Pre-training, if you remember, that's unsupervised task. Predict the next token, pick up all the contents on the web. Nowadays, we are talking about 3 trillion, 4 trillion, 5 trillion, 6 trillion tokens that are being used. And the pre-training models, they are getting alarmingly large. There was a time when if you talked about 100 billion parameter model, it looked large. 300 billion parameter looked even larger. These days, when we look at the state of the art, just to put it in perspective, this is the first week of December 2025. Gemini 3 has just been released, and it is supposed to be, from what I hear, close to 6 or 7 trillion parameter model. The Opus, the Anthropic Cloud Opus, is also supposed to be a very large model. I don't remember what size is mentioned for Opus, the latest Opus, which is Opus 4.5, I believe, isn't it, or Opus 5? 4.5. And then there is GPT 5.1 that nobody seems to know the size of, but it's also supposed to be beyond in the trillion parameter size, in the trillion, let's say the trillion parameter class. Right? These are models that we cannot even conceive of running locally. Of course, a laptop would be ridiculous to even consider. We cannot even run it on a workstation unless you are doing distilled versions of this, which are, of course, for example, for OpenAI, we have the 120 billion parameter distilled version, a small model, and then we have the 20 billion parameter small model. But the full-size model is in trillions of parameters. You really need a massive GPU investment to get it, or you need to use services like the Open Router and have somebody else host it for you. Even if they are open source, but most of them are not. In the US, almost no model is open source at this particular moment. Gemini, Claude, GPT 5.1, Grok, they are all trillion parameter class model. I'm told that Grok, the new Grok that's going to come out, will also be about in the 6-7 trillion parameter size. What Meta is up to is anyone's guess, but one would imagine that they too are rapidly scaling up in size. So let me just put it, the trillion class, trillion params, and then you bring trillion tokens. So creating a model of 6-7 trillion params and bringing 6-7 trillion tokens, that seems to be the new baseline these days. In the open source, though, the largest model that, to my knowledge, exists is the DeepSeek v3.2 that just came out, which surprisingly is the same size as the old DeepSeek R1, 671 billion parameter, not even a trillion parameter. Surprisingly, they seem to be achieving the same level of performance as this multi-trillion parameter models. So obviously they are evolving along two different axes, and the reason I mention that is it has some bearing on today's research paper reading. The direction that the open source has taken, a lot of these open source models have been taken, is to say that we have two axes along which you can get equal advancement. One way of increasing is using the neural scaling laws, and the other is innovation in research. You can innovate in AI research itself, foundational. They come up with new algorithms. Like, for example, the RLVR, GRPO, used to induce reasoning in machines, was an innovation that DeepSeek brought. But you can therefore get better performance in models using one of two approaches. The neural scaling law seems to be the favorite amongst commercial models, and the open source, probably because they don't have the hardware, have very little choice but to innovate in research itself. Nevertheless, the model performances have been getting better and better. The reason it has a bearing in what we are going to do today is the way it impacts how we think about the post-training part. So once you have a pre-trained model, we just assume that you have a pre-trained model. Now, the fundamental question that happens or that people ask is, where should we invest our resources? Should we invest a lot in pre-training? Or should we invest a lot in post-training? Post-training being the remaining step. So for example, DeepSeek took the approach that after pre-training, they went straight to RLVR. What does RLVR stand for? They gave simply put it as math and logic and coding problems. Math, logic, and coding problems. When you give this, the answers are verifiable. If you ask, Mary had 20 apples, she ate 4 and gave 6 to her neighbor. How many apples is she left with? There is a very deterministic answer that can be verified using a verifier. Likewise, if you give it a coding problem, you can write a unit test to verify whether the code is correct or not, is producing the response that it should produce, or it is not producing the response that it should produce. So from that perspective, that is the VR part of it. Reinforcement learning, RL, with verifiable rewards. Remember that when you do with verifiable rewards, it opens up enormous flexibility, because you can have math problem generator that can arbitrarily go on creating math problems ad infinitum. In the same way, you can start writing code that will generate code or problems, coding problems for a machine to solve. And in both of these situations, you a priori know the answer and you can test for it. So this is with GRPO, used GRPO, DAPO, etc. They all fall under this RLVR framework. So with that as a background, the basic question that this paper addresses is this: what really happens during fine-tuning? We do know today that if you do supervised fine-tuning, so let me park this statement, supervised fine-tuning. Supervised fine-tuning is a bit of a dangerous thing. If you bring in too much, it is the converse. For pre-training, we are told the neural scaling laws say, bring more data, bring more compute, and then you can have a bigger model. When you get to the fine-tuning part, in the post-training aspect, the game changes completely. The model size you're not playing with anymore. You have the model from pre-training. The question is, should you bring more data? Should you bring more compute? And the answer, surprisingly, is the opposite. If you bring too much data, the model will have catastrophic forgetting, or at least it will start exhibiting more collapse in significant areas. For example, it may start speaking in bilingual, right? It may start mixing Mandarin with English, or some other language with English. So between more collapse and catastrophic forgetting, there is a significant risk to supervised fine-tuning. So let me just call it a risky business. Because model can be adversarially affected, or not adversarially, adversely affected. You can have catastrophic forgetting. Models would be more collapse, means certain specific abilities are lost. Or you could have much worse, catastrophic forgetting. So, more data, more compute, both are bad ideas. And this is very counterintuitive. During pre-training, the more data, the more compute you bring, it's a great thing. But in fine-tuning, supervised fine-tuning, you have to bring just enough data to change the behavior of the model. And you have to bring just enough compute to change the behavior of the model. But you don't want to train it for too long. You don't want to bring too much data. Both of them prove wrong. So I have actually a mental...
Wait, can you actually explain a little bit about how mode collapse is an issue?
See, what happens is that when you do supervised fine-tuning, One way. So let me give you a mental picture. So suppose you have a probability distribution like this, right? This is the probability distribution of the data. You want to do a little bit more. You want to change the distribution, let us say, and in this region, let's say that you want to add a little bit here. Every time you take here, this is, see, to the one intuitive picture that I have is integral is 1, right? The total area under the probability distribution is 1, right? One mental picture to have is that you need to borrow this probability mass from somewhere. Let's say that you borrowed it from, let's say, this, and let's say that you happen to borrow it from here. Then what happens is that this flattens out. This area flattened out. Right? So this is, in probability language, you call it a mode. This little hillock is a mode. And you basically lost that mode. And what it means is that some small ability is lost. This is a very common thing. Mathematically, it's obvious that you have to borrow the mass from somewhere, right, to create a little bit of a hill here. The question is from where? You hope that you borrow it from a region that you don't care about. Suppose you're fine-tuning it for the finance domain. And let us say that your LLM lost the ability to write poetry. Not a big loss. It's fine. But you have to watch out that you don't lose that mass, that probability mass from an area or from an ability that actually does matter to you. You don't want a mode collapse there. That's the point.
Okay, that makes more sense.
That's the explanation for this. So, then, yeah, go ahead.
Mode compute?
Mode collapse. Oh, mode compute. This was mode collapse. I'm saying that in SFTP, both are dangerous. SFTP, supervised fine-tuning. If you bring too much data, the big risk with machines is that
I understand the mode data, but what do you mean by mode compute?
Mode compute means you just run many more epochs, many more iterations to the data. Okay. Let me just put it, epochs, iterations, whatever. You just do too many iterations to the data. What in very intuitive term, right? You're convincing the model that what it was thinking was wrong and it better align to the new thinking. So it starts losing ability, or more specifically. So this is what your mode collapse is, and worse is that catastrophic forgetting. Catastrophic forgetting is when what happens with catastrophic forgetting. So just to complete the picture, is that the same distribution. Why don't I make it on top of this itself? A catastrophic forgetting scenario is like some particular ability that you really care about. Let's say that you're working with finance, right? And you keep on showing it lots of finance data. It basically goes and takes, so it will become very peaked. It will become like, how should I say? It will throw a lot of mass into this very, very tall finance peak. But when you take so much mass, you're basically taking it away from somewhere. And what happens is, it may end up taking away from too many places, that kind of mass, right? And what you start noticing is, significant abilities are gone. So this is the phenomenon of catastrophic forgetting, right? And it is very real. It's the one thing that you're absolutely paranoid on when you do supervised fine-tuning. And the mathematical explanation is obvious. Nevertheless, I mean, see, when you think in terms of priority distribution, it's very straightforward to think about it. But when it happens, it's very unpleasant. Right? You notice that it becomes super specialized for finance. It can only answer some few areas of finance with genius level intelligence. But everything else, like core general ability, it has lost. Right? Go ahead.
Can you say that catastrophic forgetting is overfitting for LLMs?
Catastrophic forgetting.
Is that the equivalent of overfitting for LLMs?
Let me think about it. Is it like, no, it is not caused by overfitting per se. In a way you can say it's overfitting to a very niche domain data.
Right? Overfitting in terms of the concept that how we are going too much in specific for other data that we are training with. and then probably in this case the data that we are fine tuning with, so that
See,
in sense of the
directionally it's like that, but we don't think of it like that. Overfitting in machine learning has a specific meaning. The band gap between eval and test loss, training and eval loss expands. So what you notice is that your training loss is falling, but your eval loss is increasing, right? That would be considered overfitting. But here what happens is, in a way, it is in spirit, directionally it is overfitting.
Just not with the exact nuances of it, but just
directionally it's like that. Directionally it's like
that. The fact that you're working too much towards one domain.
That is right. What it is basically saying is that I am seeing this new data. Let me achieve perfection on this new data, because the loss function with which you are putting gradient pressure, back pressure on the model is only with this new data, finance data. So obviously it becomes very good with the finance data. And on finance data, if you look at the gap between the training and the evals, it won't show any obvious overfitting. But for general data it is. General data now has collapsed. Right? That's the problem of catastrophic forgetting. Right? So actually this paper goes to the heart of why it happens. No one really knew why it was happening. So and that's why I find that this paper, which goes to one of the biggest problems, in fact the biggest problem with supervised fine-tuning, it finally unravels and comes up with an explanation of what's going on. And I find that unbelievably, not many people seem to have noticed the relevance of it. So so that is supervised fine-tuning with its risk. So the main point is, in supervised fine-tuning, you bring less data and less compute. But then when you do RLVR, paradoxically, there are two paradoxes that show up. First is, when you are doing reinforcement learning fine-tuning, RLVR fine-tuning, then reinforcement learning, by its very nature, is rollout inefficient. The reward signal is so weak. Reward as a signal, it's a scalar value. It is, remember that if you have a reward of a trajectory, which is that, in very common sense terms, the machine says the answer, Mary now has 11 apples, and it is wrong. You don't give it enough reward. But if the machine says that no, if Mary ate 4 apples and gave 6 to her neighbor, then she has 10 apples. Then you give it a positive reward. But you don't tell it what it did right, and all you say is you're right, right? And you let it. You basically say whichever way you arrive to the answer was right, because what matters is the answer, and the answer is right. So it's a scalar reward, especially of the trajectory, is a scalar signal. And that scalar signal has this big attribution problem. What step that it take, which taken generation sequence, in intermediate steps did it do right, which ones it didn't do so well, you don't know. So you have an attribution problem of how do you attribute that reward across all the steps, good or bad, in arriving at the answer. So because of that, reinforcement learning has always been noisier because of the weaker signal. And because of that, it is rollout inefficient. Means, in common sense terms, you have to do lots and lots of rollouts. Means you have to keep on training the model. So now, when it comes to reinforcement learning and with verifiable rewards, you have lots of compute. And the surprising thing is, those lots of computes, they don't lead to they are less likely, or almost not quite likely, to have the same degree of risk as supervised fine-tuning, right? Supervised fine-tuning, if you ran it for, let us say, even 1,000 epochs, let's say, forget 1,000 epochs, 2-3 epochs, you begin to get scared. You say, maybe it's enough, right? But if you're doing RLVR 5, 10, 20,000 iterations is no big deal at all, right? So that may mean many, many epochs through the data. And that is perfectly fine, and it doesn't somehow tend to risk catastrophic forgetting or mode collapse as much as the risk of supervised fine-tuning. And so the first mystery is why? Why is RLVR not prone to destroying the model as much as, let us say, SFT when given more data and compute? In fact, it's the other way around. You do need a lot of compute to make it work. So this is a big question. And this paper resolves this question. The other question that you struggle with is that people have struggled with is a discovery that people made, which is even more paradoxical. People ask this question, if RLVR, deep sea carbon paper, if you take at it, they showed that you can induce reasoning in machines by reinforcement learning with verifiable reports, RLVR, GRPO. That is fine. First thing is, it's startling. To induce reasoning in machine was the holy grail of artificial intelligence, isn't it? For the longest time, would you consider a person intelligent if the person cannot reason? You wouldn't. And yet, the LLMs and all of our models, they were very, very weak reasoners. You did all sorts of tricks like trying to train it on chain of thought examples, trying to put chain of thought in the prompt itself, right? It was basically monkey see, monkey do, or monkey see, monkey do something very similar. That was the approach that we were taking with LLMs. And then came RLVR with the deep sea carbon paper. And basically what they said, you don't need to do any of that. All you need to do is to sit back, relax, and let the model discover its own reasoning modalities. And spontaneously, reasoning, that holy grail of AI, on its own emerged, which took everybody by surprise, including the researchers in DeepSeek. Right? That how can you go ahead?
Was reasoning completely latent then?
Was reasoning completely latent?
Yeah. Was it like a latent ability just completely then?
So and this is one of the things that this paper will go into. So why is it that was it already there in the pre-trained model? Did somehow RLVR put the last piece in the puzzle to awaken that reasoning? Or was it a fundamental new induced ability? It's a very active area of research. Actually, 1 month ago, I did a paper reading which seemed to imply that reasoning ability is generated in the pre-training process. How to use that ability is missing. And what RLVR does is, it teaches the LLM the strategies to use that reasoning ability. Right? That's one of the hypotheses. It's one of the papers we covered a month ago. So obviously, I don't think that there is a general consensus. The research community is still in a very exploratory stage on that topic. But nevertheless, that's where we are. So coming back to it, this is a fact, right? Reasoning is a pretty profound ability, and RLVR induces it. So one would imagine that core new abilities would change the model parameters radically. Isn't it? Isn't it a common thing? You suddenly see that the model is able to do something that was really hard and it couldn't do it. And it is able to do it. One's expectation would be that the parameters of the model, if you think of the model as f theta, this must have gone through radical change. And then here comes the paradox. let me write paradox properly. Paradox. The paradox that people discovered is, and researchers like Banerjee et al. Discovered in a prior research something, and there were other people who were discovering the same thing, that when you actually go and look at the parameters of the LLM, the number of parameters that actually go through substantive changes is minuscule, right? You would imagine that at least 80% of the parameters would have changed substantively, but actually very, very few parameters change. Very few parameters go through significant change or change at all. So how is that possible? How can you, it's almost like, you just take a screwdriver and go into the engine and you tighten a few nuts here and there, and all of a sudden the engine has a completely new ability, right? So that is the paradox that people had already discovered, and they were all very puzzled. There's something very mysterious going on. How come RLVR is not so susceptible to cause mode collapses and especially catastrophic forgetting? And how come not much changes? Without much change, how can you induce such significant abilities? So these two paradoxes is what this paper resolves, and it resolves in a what I felt was an amazingly elegant manner, a really elegant way it solved it. So I suppose one should have expected, coming out of the Fair Research Lab, Metal Lab. And they give an analogy. So with that as a background, let's go and read this paper. Any questions, guys, before we get it? So this is the background. I was just trying to set up the background that would make this paper relevant or make sense. You realize that these are big problems, right? Big things that we didn't understand. And this paper is going to talk about it. So any questions, guys, before we start paper reading?
Wait, can you just give like a
Yeah.
Go ahead, sorry.
No, go ahead.
Could you just give like a high level summary as to like how it's slightly different, like what we're fixing from RLHF that RLVR is kind of helping with?
Okay, so you want me to first give you what the paper actually says, what it finds? Okay, I can give you the findings, the core findings. What this paper finds is this. It comes up with 3 gates. Let me just mention the 3 gates that it says, which are, one is that if you do RLVR, you must have something that is KL divergence or equivalent as tether. What it means is that the model that you started out before the RL, the pre-trained model, let me call it the PyRef, right? Then, and the model that you end up with, that you go through the process of, as you take the model through the process of reinforcement learning, the KL divergence. What is KL divergence means? How much this probability distribution changes. KL divergence is a measure of the change, right? How far the new model is as a policy. In reinforcement learning, people use the word policy, but think of it just as the parameters of the model, right? Model as a function. So KL divergence is a measure of how far the new model is from the model before pre-training. And what you do is you bound it. You can bound it either with an explicit, like a tether. You can say that this is the trust region, policy, optimization, TRPU. This is an older way, which put an explicit tether. It basically said that if this is pi-rem, put a circle, you have to be within this circle. This is the circle delta. Your pi has to belong to this region. Let me call this region R. This disk region R. So pi theta must belong to this region R. Right? This is a pretty hard constraint, GRQ. Then came proximal policy optimization and many variations of it, which actually used a clipping argument, a local change argument. Then came GRPO, this is the PPO. PPO, by the way, the initial GPT was built off PPO. Then came the GRPO, the RLVR, the approach taken by DeepSeek. This is the GPT, the original GPT, chat GPT approach. Then came DeepSeek approach, DeepSeek R1 approach. And what they did is they brought back the thing, but they brought it back as a sort of a Lagrange multiplier. They said that we don't put a very hard limit, but we put a tether. But nevertheless, they all put a tether that don't go too far from this. Then came DAPO, all of these, doesn't matter. There are many, many variants of this. But bottom line is, the first finding is that you must, in the fine-tuning, use scale divergence to put a tether. Fortunately, all of them are doing that in different variations. So the paper shows that equivalently they are all doing very similar things. That is the first, they call it the gate one. Gate number one. Then they come up with, and then I'll just jump over gate number 3, the 2, and I'll go to gate number 3, which is easy to actually explain. They say that the apparent sparsity of parameter change, it claims, is a precision. Think of it, what I call it as a precision-induced mirage. What it means is that, of sorts, what they are saying is that in RL, it isn't that the parameters of the model don't change, but at each step, because the signal is weak, right? The reward function signal is weak. So the parameter changes are so tiny that, broadly speaking, and this paper goes into the details, which is the gate number 2, that there is actually a pretty large change. But because we are using a float 16, you know, the floating point precision is float 16, right, during fine-tuning of the model, then what happens is, if the change is below threshold, right? One intuitive way to say it is that, suppose something could remember only to 2 decimal places. Of course, float is much more precise, but just for the sake of analogy, then if the value happened to change from 2.51 to 2.153, as far as the machine is concerned, it will still store the value as 2.15, and it won't register any change. It won't see the change. And they prove it by doing 2 tricks. One is they boost the learning rate. If you boost the learning rate, alpha, then what happens? It forces a larger jump. So all of this sub-threshold change, they become visible. Right? Now you can see those changes. The other, so method 1, to prove this, and the method 2 that they use to prove it is, they say, okay, what if you went to float 32? Now you have more precise arithmetic, isn't it? You get more decimals to work with. And the moment they went to float 32, they clearly showed that actually change is happening. You could see the change, right? And so they say that this big mystery that everybody is worried about, that only so few parameters in the model are changing, that is actually an artifact of the fact that we are using float 16 rather than float 32. And the fact that by necessity, you have to use small learning rates. Go ahead.
So it's just using float 16 as a filter?
You work with float 16 in fine-tuning. And so that's what's causing it. right? So now comes the paper's crux, which is actually gate number 2. They use this metaphor of gates. They say that the explanation of all of this is through 3 gates that help to explain. Gate 2 is the most mathematically involved and actually the most beautiful thing that they say. So now the question is, why is it that some parameters change big and others parameters don't change much? That's the first question. The second question that is there is that why is supervised fine-tuning dangerous? Like very easily it gets into trouble. Whereas RL you can coast along for a very long time with a lot of rollouts that despite its being inefficient, it tends to awaken such powerful abilities like reasoning. What really is going on there? And that is the crux of this paper. And that's what we're going to. And what they say is that, and again, just to summarize the research, what it says is that if you, so I wish I could do that. See, imagine a hill. So imagine that, how does a sand dune look? Okay. So here is a sand dune. So it doesn't use the metaphor of sand dune, but I'm using it because I find that when I think in terms of any probability distribution as a sand dune, it sort of makes more sense. Even the idea that probability mass is conserved is obvious, sand is conserved, kind of a reason. So now, what it is saying is that, see, crux of it is, look at this point. If you are here, this is the direction of high curvature. This should be obvious to any of us. For example, if you just happen to go to the beach and you look at the sand dune, if you're driving down to Monterey Bay, for example, you along the coast you see all these sand dunes. In one direction it will be rather gentle, like this direction is rather gently sloping, and this direction is gently sloping. But there'll be one direction up the sand dune, straight up the sand dune, that will be very steep, very high curvature direction. Does that feel intuitive, guys? We have all experienced that. And so, what the main finding of this paper, which actually, in my opinion, they have written it in a very formal and mathematical way, which is good, but it makes it a little bit opaque, and you have to know quite a bit of math to get the final intuition. But basically, what they are saying is, gate 2 finding is that KL divergence, and this is a fact that people know, that if you have a KL divergence for small changes, right, theta plus delta, if you just make a small change to a parameter, which is exactly what you want, then you can expand this, can be written as basically a change in the parameters of the model. There is something in mathematics called a Fisher information matrix, F matrix, and delta t, delta theta. It's basically, this is called, and this is literally the Riemann curvature. Geometrically, it is the Riemann curvature. It is literally the Riemann curvature, right? Or those of you who have the physics background can think of it as, the one intuition that you have is, it is g mu nu dx nu. And this will immediately recall to you that this is, you're looking at the curvature on the Riemann manifold at that point, right? If you want to go along a certain direction, how would you do that? So this is it. This is the Fisher. So this is a fact, by the way. It has to do with the KL divergence, which is why the KL divergence is so important in RLVR. Some manifestation of KL divergence, either KL divergence directly or something that induces a similar behavior to KL divergence. Because KL divergence locally for small changes for small changes can be written in terms of a Riemann curvature. What is this Riemann curvature object? Geometrically, it is literally this. It is literally the curvature. It will have directions. If you look at the directions of the Riemann curvature, it will tell you in which direction things are steep, like changing, there's high curvature, and which directions are flattened, right? Like as in a sand dune, these directions are much more gentle, and some directions are flattened. So if you take this Riemann curvature, which is a square matrix, and you do its eigenvalue decomposition, which is a mathematical construct, but I'll just make it very obvious to you. In case if you don't recall your eigenvalue decomposition, there is a simple intuition to remember. If you take a unit disk and you apply it with a matrix, you will notice that any matrix will convert this disk into either another disk or in generally an ellipse. Right? The disk will become an ellipse. The moment it becomes an ellipse, it has principal directions. Let's say U1 and U2. The direction of maximum stretch and the direction of minimum stretch, or rather shrinkage. Right? Because you're taking a disk and you're elongating it in one direction, and necessarily, because again the conservation of mass, you're shrinking it in the other direction. Right? Now, it will always have this. These are called the eigenvectors. These are the eigenvectors. And the degree of stretch are the eigenvalues. Right? Oh, sorry, what just happened? Yeah, these are the eigenvalues. So this is something we are taught in our linear algebra class, but basically this is the intuition. Any matrix will take a disk and do that. A square matrix will do this. Now, so therefore you can say that that matrix is uniquely defined by its eigenvectors and eigenvalues, or characterized by that. And which is why then there's a mathematical sort of the machinery that says that M can be written as UD, U transpose, where U is made up of the unit vectors U1, U2, and D is lambda 1, lambda 2. Right? And so there's a bit of mathematical formalism, but the geometric intuition is very obvious. So to the extent that this the Fisher information matrix, and therefore the Riemann curvature matrix is a square matrix, therefore you can validly ask for its eigendirections, eigenvectors. The biggest eigenvector, the direction of the biggest eigenvalue are called the principals. Right? So the one with the greatest stretch is the principal direction, and other directions are the lesser ones. Right? So there will be a situation like lambda 1 is greater than lambda 2 is greater than lambda 3. Typically, and these lambdas, they tend to show power law behavior. Like typically, if you plot out the lambdas, you will notice that they fall. The big lambdas are here, and all the other lambdas are tiny. Right? So these are your principles, principal directions. The big principles, so from which comes the principal component analysis, for example, the PC of machine learning. And what this paper says, at heart, the gate 2, which is the heart of this paper, which explains everything, except for the sparsity, gate 3. Gate 1 leads to gate 2. Gate 2 is basically saying that SFT, unfortunately, tends to supervise fine-tuning, tends to go aggressively in the direction of the curvature. Whereas RLVR tends to move sand along the smoother direction. So when you are sort of moving sand along the smoother direction, what are you doing? You're just flattening out small little hills, right? Bumps. You're just flattening small bumps. So if you're continuously going perpendicular to this steep curvature direction, but going along the smoother directions, right? Then you're not making much change at every iteration, right? And so you therefore risk catastrophic forgetting much less. And another way to look at it is, if you go along, what SFT does is, because the signal is so strong, In supervised fine-tuning, you tell this is the answer, right? In RL, you don't give the answer. You just say, if you happen to be doing things right, I'll give you a reward, right? But in supervised fine-tuning, the signal is so strong, it sort of tempts the model and it causes the model to aggressively go along the high curvature directions. And in doing so, the mental model is, as with sand dune, you go digging along the steep side, you can have the whole sand dune collapse on you, right? Which is the, I mean, at the end of all the mathematics, that is the gist of what this paper is trying to say, that SFT risks more, is faster, but it risks more because it goes along the directions of the principles of the curvature, the top eigen directions of the curvature. And therefore the title of this paper, which is The Path Not Taken, RLVR, provably learns, and this is the part, learns off the principles. Off the principles means it stays away from the very high curvature directions. Instead goes along the gentler planes, right? And obviously the subtext of this is that RLVR avoids those directions, but SFT, supervised fine-tuning, does not. Hamad, go ahead.
So does RLVR like mechanically steer away from the principle?
Yes, that's exactly what it is, right? And there is a whole mathematical, actually I realize that we are almost out of time. I would have liked to read the paper more carefully, but I suppose it's a dense paper, and so let me go with just this. And the first picture is very illustrative. See, if you look at this picture here, what it is saying is, imagine that there is a hill. I mean, this picture is not perfect, but it's a pretty good analogy. If there is a hill, a target there, the target may actually be behind the hill, even though it appears as though it's planted on the hill, right? And so I'll just read this thing. Figure 1. SFTP follows an externally guided route traversing high curvature directions over the mountain to reach the target. So if you notice, it is going straight up towards the target, right? Which is the direction of high curvature, right? It's like going up to Mission Peak straight on. By the way, for those of you who are not here in the Bay Area, Mission Peak is a hill right behind us here. And it's a hiker's paradise. Every morning there's a traffic jam. So many hikers are on the trail. And what they are saying is that RLVR, without an explicit feature, behaves as if steered by an implicit compass, taking a low curvature route. That is all that this paper is saying. It is saying that if you look at this, it is almost going, you notice that it is taking a gentler path to the target, not trying to go uphill to the target. It's almost as though having a compass, I suppose, is a metaphor for saying somehow it knows that that flag out there is not on the hill but behind the hill, and it can gently go around the hill. Right? So that is what it. That's what it is. It is, and actually, as always, these days, the papers that come out which have heavy math, they tend to put all the math in the appendix. But since math is the biggest discovery of this paper, it is interesting that the main discovery is sitting in the appendix, right? And here it is. And obviously, there's a lot of data to back it up and so forth. I found this paper. I suppose because it's very mathsy, it's not getting attention. But the crux of the paper comes out in this. So obviously there's a lot of talk about M projection and the tilting oracle and so forth, the jargon that we use in reinforcement learning quite a bit. And actually, it is not, we are all used to seeing this in GRPO, PPO, etc., all of the policy. Like this comes from the old theory of the 1992, since 1992, ever since the reinforce algorithm, we have always been seeing this ratio function, the pi theta over pi over. Basically, it says that it's the importance ratio. If I make this change to the model, how advantageous is it? How much how much reward will I get? It's the theory of the model. So looking at that, and I'll just skip it because I apologize for those of you who are not familiar with this paper, with the reinforcement learning language. But this is so you literally see this. This is the main lemma. This is what I was talking about, that all things considered, where am I? Let me take a color that will look reasonable here. This is it. This is your theta change. Theta. So you're basically saying that the Fisher information matrix is this. And this actually is, and this you have to know a little bit, that this geometrically is related to the Riemann curvature. I don't know where in the paper it says that, or it doesn't say that, but it is that. And I think it says that somewhere, I forgot where. But this is the main finding of the paper, proof of the proposition. So yeah, this is it. This, by the way, is known now. It builds upon that, and it shows that if you take the eigenvalue decomposition, you do all of this proof of gate 2. See, here's the thing. So it goes to the whole proving and so on and so forth of this. The proofs are very condensed, so this paper makes a little bit of a hard reading unless you're already familiar with the mathematics of it. And that's all it is saying. So, guys, I could do, I suppose it's already 8:10. We are almost out of time. It's far better that I take questions now. I don't know, did I convey the main idea of the paper clearly, or was it too opaque? Is anyone remote has a comment, guys? Oh, is there anyone still there? Yes, people are still here. Guys, any
question?
Go ahead.
What's the difference between RLHF and RLVR?
Oh, RLHF is reinforcement learning based on human feedback. So, for example, when you look at PPO or these techniques, what you do is you get human feedback on the answers that the LLM is giving, and then so one of the things, for example, how was ChatGPT trained? What you did is that the Instruct GPT pipeline says that first you create a reward neural network whose job is to learn how humans give rewards, how humans give feedback, and then make the main model try to extract the maximum reward from the reward model. Right? It's a very indirect process, but it is completely based on human judgment, right? Human feedback. RLVR, on the other hand, says you don't need a reward function at all. If it is a math problem, answer is absolutely incontrovertibly and objectively known. If it is a coding problem, you already know the answer, right? So the so-called reward function is not a neural network. It is a deterministic simple program, right? A solver, a math solver, or a Python unit test, for example, right? And so you use the reward generated as an indirect effect. It's the group relative, which basically means z-score. The z-scoring that you are familiar with, bell curve, being graded on a bell curve. That's the core intuition of GRPU, the first of the RLVR papers.
Okay.
So that's the difference.
So since we have a deterministic answer, we don't want any human intervention over there. Only
yes, that's the main thing.
Okay. So we just have to verify that through a neural network you are doing that verification.
No, the verification is no. You don't need a neural network. You just use a simple program solver. For example, a unit test. When you write a unit test in Python or Java or C, there's nothing neural network about it.
Okay.
It's just a program. Yeah. You plug in the answer. Exactly, automated testing. Okay. That's all it is. Yeah. Okay. In the same way, a math solver is very easy. I mean, you just know the answer. And you just say, hey, because I know the answer, if you get to this answer, I'll give you a positive reward. If you don't get to it, then oops.
Okay.
That's it.
Okay. Thanks. Asif.
Yeah. Anybody else, guys? Any other question? Yeah, go ahead, Ahmad.
The paper said that like their words was there's an implicit compass that steers away from principal directions. Is that all?
It's because of the reward function. It's because of the way RL works. The KL tether, that is the KL tether. What it says is that because you have the KL divergence, and because KL divergence was small, because of the tethering effect, factorizes into the Fisher information matrix, which is nothing but geometrically the Riemann curvature. So the end effect is that it is just steering you off principles continuously. The KL tether is the compass. Right? Anyone else, guys? Any other feedback before we close today? Oh my! I get the feeling that I lost everybody. It was perhaps too obscure a paper or obtuse a paper. It's a beautiful paper, guys. I don't know why am I so excited, but to me, it solves a lot of questions I've had in my mind for a long time, right? And anybody would have, why is SFT so dangerous? Like, why do you have to be so cautious while doing supervised fine tuning? Why can I take liberties with doing reinforcement learning with VR? Right? And the explanation seems to come out from this. All right, guys, since there are no more questions, I apologize if I didn't explain it quite well. Yeah,
no, I think it's pretty obvious once you explained it. It seems obvious enough. So when we do the VR part of it, right? So
yeah.
Is it initially you mentioned math and it's math and computer science kind of things. It is quite verifiable.
Very verifiable. 100% verifiable.
But can it be applied to other fields like I don't know?
Yeah. So what people do is, so long as you have some way to verify the answer, you can apply it. If you think about it, the GRPO is silent about what your verifier is. It is totally up to you. For example, you could use just another LLM to give a score, and GRPO would not know. It will say, okay, fine, you just gave me a number, I use that number and run with it. Right? I can create a relative reward from that, as a bell curve from that.
But that would be similar to the RLHF kind of thing, right? Still,
that's the whole thing. That if it's also a question worth asking. In
that
RLHF also, right? Why is it that you don't have so complete mode collapses or catastrophic forgetting? RL somehow seems to be. See, the problem with RLHF is because you have a reward model separately. Well, I take that back. RLHF itself has variations. If you do direct preference optimization, you don't quite do it. You take human feedback and you directly treat it as almost like a contrastive loss situation and supervised contrastive loss kind of a. So it uses the RL machinery but does contrastive loss, right? That's sort of like a direct preference optimization. It has a flavor of that. But if you do proximal policy optimization, and the way initially, for example, GPT 3.5 was trained, what they did is they built a neural network that's a reward model. The problem with that is what is called reward hacking.
Right.
The neural network doesn't know that it's hacking the reward, it's cheating the system. It has only one goal, to maximize the reward from the reward network. But if the reward neural network has any weakness, the LLM will end up exploiting it, which is the unintended consequence of having a separate reward neural network. And that has always been a problem with PPU, proximal policy optimization, right? The older ways.
Okay. Yeah, so to me, it seems like the reward function or the reward methodology in this one is very deterministic, but when it is not, then we may not be able to achieve.
So this paper, if you notice, it's very strictly used to one particular methodology. It says RLVR. It says what happens when you do RLVR, right? And the broader message is whether we do RLVR or not, we at least have a good understanding of why SFTP, supervised fine tuning, is so scary. It's like, see, we do it all the time, right? You do it. After a little while, all it remembers is the new data. And the only thing it works well is on the new data. The old data the performance actually degrades. Right? So that's that. Right? So all right, guys, am I still there on Zoom? Samantha, am I still there on Zoom?
Yes, sir.
Okay. All right, guys, any questions from anyone? Oh, nice, Murli. Yes, do read it, Murli. This is really a beautiful piece of research. And I do feel that it's sort of under noticed at this moment, mostly because it is a little bit mathematically nuanced.
Were there any kind of like high level numbers in terms of like what kind of improvements it saw in terms of like getting rid of catastrophic forgetting or like the other issue with them?
See, this is more what I call a conceptual breakthrough. It is not saying that we have a new method, a new way for you to do things.
Oh, okay. It's just conceptualizing.
Yeah, it is conceptualizing and explaining what was a paradox. Isn't it paradoxical? Why is RLVR proving so safe? Like we go on, it's very inefficient, signal is weak, but one bonus that we get is that you don't. If you did that with SFT, supervised fine tuning, you would end up in a disaster pretty soon, right? But here you don't seem to be. That is one thing. The other lesser mystery that it solves is when you induce reasoning in a model, it's a big deal. I mean, it's the holy grail of AI. And yet, so few parameters in the model have changed. What? How did that happen? Right? That would be a natural reaction. It goes against intuition, right? And the explanation it gives, which is this gate 3, it says that, hey, it isn't that they wouldn't change. It's a computational artifact. The fact that you're using float 16, those changes are sub-threshold for float 16. Try using float 32 and you'll start seeing that a lot more parameters change. Right? Or just boost up the learning rate and you'll notice that a lot more parameters change. Right? So it ends up unraveling 2 mysteries. That is its main contribution. And yeah, I must say that this paper can be a bit dense because when it says, for example, that RL rotates less, it is a spectrum preserving in the spectral analysis sense. What exactly are they talking about and so forth? So it is, in a way, like it is talking to an audience that already knows all of these terms, right, and is very familiar with curvatures and eigenvalue decompositions and so on and so forth. Right? But the main contribution, which is this, a mechanistic theory of RL's unique optimization dynamics. Like, why is it that RL works? And it says gate 1, the fact that you have a KL leash, its consequence is that when you work through the whole grind through the math, you realize that you end up with a Fisher information matrix, which actually somewhere they must be saying about the curvature part of it. They do, I'm pretty sure. Yeah, high curvature directions. These high curvature, I don't know if they use the word Riemann curvature, but it is the Riemann curvature. Right? Geometrically, it is the Riemann curvature. You know, one intuition of the Riemann curvature is, think of a globe. Globe is the quintessential Riemann surface, and the curvature on the globe is very very apparent. Right?
I think the main question it addresses is the box a little bit on the scroll down.
Scroll down.
No, the other way. Yeah, that where does the optimization bias?
Yes, exactly. And how does it shape the parameter? Oh, sorry. What did I just do? Control. Oh no, I zoomed in, zoomed out, God knows what I did. Hang on. Let me post this. Oops, I ended up in a completely different paper. I apologize. A path not taken. Yeah, this, I'm sorry. Oh, gosh, I'm being an idiot. Okay, here. Where does the optimization bias originate? Like, why is it that RL behaves very differently from SFT? And why does SFT behave the way supervised fine-tuning behave the way that it does? And why does RL behave a different way? And it says, and at the crux of it, see, the beautiful idea is very simple. The moment you put a care leash, a tether, it's like a dog on a leash, right? And the moment you do that, now you have tethered how far your model will go from the reference model. And the impact of that is, it only takes the smoother paths. Oh, there's a comment. Let me read that comment. And once again, where did I lose the? Is the? Oh, there we go. Oh, thank you, Krishna. Alright guys, if there's nothing else, I'll end today's paper reading. Thank you for being part of our Support Vectors meetup and paper reading series. If you do have some paper to suggest that we cover, please do so on our Discord channel, the public Discord channel. And Samantha, perhaps you could post the Discord channel for the people who are new.